Hi everyone, my name is Jason Clark and I'm going to talk today a little bit about our corn fertility program and some of the updates we have with phosphorus and nitrogen. We might hit on potassium, but our focus is going to be on phosphorus and nitrogen. So the goal of today is really to know a couple things about soil testing. A simple thing we can think about is we have our corn yield potential of about 200 bushels per acre in a field, and we know our soil test levels are phosphorus 10, potassium 120. Then based on those, we can know we can put 52 pounds of PTO5 per acre, 60 pounds of K2O per acre. We also want to know that if our phosphorus levels are 18 parts per million Olsen and 160 parts per million K, then our fertilizer recommendation rate for those would be 0. So today's goal is to kind of help us understand how we get to those recommendations and better understanding of what goes into getting these recommendations out to people. So a lot of this research is based on information in both central and eastern South Dakota. You can see the different sites here. We've added some data the last few years, and we'll keep adding to the data set to kind of enhance it and grow it as we go. But this is kind of what we want to know before we apply phosphorus and potassium. The first question is we want to know what extractant did they use at the lab? Why did they use that extractant? What is the soil test amount from that extractant? What's the likelihood that my crop is going to respond to fertilization? And if it will respond, what rate should I apply? And also, when we're talking about just about soil sampling, what depth should we sample at and why is that important? So first of all, I'm going to look at phosphorus. Here, this is kind of the outline we're going to look at with soil test phosphorus. We're going to look at what is an extractant, why are there so many, doesn't matter which one I use. We have Bray, Olsen, Malik, and there are several others. And really what these extractants are doing and why there are so many is if we imagine a corn plant here and we have these bits of phosphorus in the soil, those plants will send out roots. And as those roots go out, they'll take in that phosphorus. And then over time, as those roots continue, they'll continue to take up phosphorus. However, there'll still be some phosphorus left in the soil, and what these extractants are doing is they're mimicking what that plant is doing. If the plant root was there, how much phosphorus will be available and extracted, and that's what these different extractants, the people who have come up with them, that's the Olsen, the Bray, the Maliks, those tests, that's what they've come up with to help mimic what that plant does. So that's what those extractants do, is they really measure the amount of nutrient in the soil a plant will likely take up. So that's what we're mimicking, what we're trying to measure. So that covers that part there. It's really looking at the nutrient availability in the soil. And the next question is, we do this, so why are there so many? And then we'll cover, does it matter which one I use, Bray, Olsen, Malik 3, things of that nature. So we're gonna answer this question about does it matter which one and why are there so many based on a project that I did a few years ago. We're gonna look at a field up here in northeastern South Dakota. And this field, this is just in one field. We have 4 different sampling areas that we looked at, and we're going to look at some soil test levels here. That all these spots are within 100 yards of each other, even closer, really. So here, we're going to look at these things right here, and we want you to pay attention mostly to this blue bar here. This yellow bar represents the critical value, so this is Bray phosphorus, so the critical value is 21. So it's showing here a Bray phosphorus value of 0.9, and if we travel over and a K of 120, sulfur of 13, so we kind of see those for that spot right there. So we're going to move to the second spot here, and here again we have our phosphorus, the blue bar, 0.9, the K of 148, the sulfur of 8.2. Travel down a little bit farther, phosphorus of 1, K of 104, sulfur of 8.2. We're going to move over to the fourth one. This is a little bit lower lying area here, and we hit now phosphorus of 26, K of 157, sulfur of 11.8. So what's the difference here? We haven't moved that far. In the field, we should expect some phosphorus differences, but here if we look at these phosphorus differences, we go from 0.9, 0.91 to 26. So the big thing that we're missing is pH, because pH controls what these extractants can find. So here we have a pH of 8.2. The second spot we have a pH of 8, then 8.1, and this fourth spot where we have a phosphorus of 26 instead of the 0.9, 0.9, and 1, here we have a soil pH of 7.8. And that's important to know because Bray phosphorus is sensitive to pH. In higher pH soils, as we can see here, the Bray does not do very well because of the high calcium carbonates in the soil. Whereas if we get a lower pH, below 7.8, some people give you a cutoff of 7.2. But here 7.8 still showed up much better of 26 because the phosphorus, the field didn't respond at all in any of these spots to phosphorus application. But using the Bray test, we wouldn't be able to find that. So it's important that we able to use the appropriate test. So if we look at this Bray phosphorus of 0.9 right here, pH of 8.2, this is our first spot in the field. And then we look at our Olsen phosphorus as 20, so you can see the much sizable difference between these. In high pH soils, Olsen phosphorus is able to extract the phosphorus from the soil much better than the Bray test. So second spot, 0.9, Olsen phosphorus 18. Third spot, Bray phosphorus 1, Olsen phosphorus 18. Fourth spot, Bray 26, Olsen 22. So you can see they're both above their critical values of 21 and 16 when we use the appropriate soil test. So at high pH soils, the Olsen test is really important that we use this test right here for it, and this shows a really good reason of why. So if we look at a little bit more detail, and this is coming from Iowa State University, I don't have information on this specifically for South Dakota, but the trend we can see is pretty similar for these other sites. So if we look at Olsen and Bray for pH soils of 7.3 or lower, we have a pretty good correlation there. If we look at Malick 3 versus Bray 1, 7.3 lower, decent correlation. That line's fairly good. The points are around that line. Look at Olsen versus Malick. It's pretty similar, decent relationship when we're below this 7.3 right here. However, when we get to soils pH of 7.4 or higher, we see what we see in the last one. We see, there really isn't a very good line. We have a bunch of points that go straight up. We have one that's over here. There's a little bit of relationship, but it's a very much weaker relationship. Now, if we look at Malick versus Bray, it's even worse. So a lot of times we're starting to get a lot of people in a lot of labs using Malick 3 because you can use it for multiple nutrients. However, in higher pH soils, Malick 3 soil testing is not the best. Versus Bray doesn't really correlate very well. And Olsen versus Malick is better because Olsen does better in higher pH soils. Malick 3 does do okay in Iowa. We've seen some, if we have higher calcium carbonates, I know in western Minnesota they've had some issues with the Malick 3 test, and we're trying to work on some projects to look at this, what this looks like here in South Dakota. So basically, as pH increases above 7.4, the Bray 1 test is much better, and actually, the Bray test underestimates the available P, whereas the Olsen and Malick can do a better job of estimating it. So this is really the same thing, turn 40 soil samples from farmers' fields. pH is less than 7.5, 7.05 to 7.45, and then 7.45 to 8.2. See the relationship is decent when we're below 7.05, a little bit higher. Our R value, which is this right here, goes from 0.77 to 0.62. When we go to higher pH soils, we lose that relationship, and we can see these high pH soils above 7.4, using that Bray phosphorus isn't a good idea. If we look at Olsen and Malick, you kind of see that same trend, or that same trend kind of goes away as below 7.05 are 0.79, 0.67, above 7.4 pH are 0.81. So it's showing those Olsen and Malick 3 do better in higher pH soils. So that's kind of this first part. We've talked about what is an extractant, why are there so many? There are so many extractants because people are trying to find the best type of extractant. for different types of soils. So we can see the Olsen does better in high pH soils, the Bray does good in lower pH soils, and Malick does good in both low and high pH soils. It does have some issue in some higher calcium carbonate soils in western Minnesota I've seen, and we're working on some research for South Dakota to see what it looks like there. So it doesn't matter which one. Yes, we've already seen, Bray and Olsen in low pH, Olsen P in high pH. And we're looking at why no Malick 3, why don't I recommend it? We just haven't done the research in South Dakota, and the research that I've seen, it's messy. And so the Olsen P is actually a better indicator so far of data. We're working on some research to see if this still holds true over time. That is something we need to, I'm still working on getting the data together to see that. So for now, it's really important for farmers to understand what test their lab is running, so then they can correlate that to their recommendations and make sure they're getting the best recommendations, which is really important. So that's the first part of what extractant they use and why. So the next part is we want to know what soil test amount do we have and how likely we are to see a crop respond to fertilization. So here, if we look at our soil test results, we're looking for our value. We have an Olsen P of 12 parts per million. The Bray P is blank because we didn't run it. In this case, because we used the Olsen P test. So in our Olsen P, if we have 12 parts per million, what's the likelihood we'll respond? And if we look at our soil test categories here, we have our very low to high with our different Olsen P and Bray P categories. And here, the important thing is these are really based on the very low or very high is based on our likelihood to respond. So very low, 0 to 3, 0 to 5 is 80% likely to respond. Very high is less than 20% likely to respond. And if it does respond, it's likely to be a pretty low increase in yield. So yield response frequency, if we look at data in South Dakota, it decreases as soil test P increases. So if we look here on this y-axis, we have our corn yield response frequency going from 0 to 100%, and our soil test phosphorus low at 0 going to high. If we look at the data here, we can see kind of what we typically think is that as soil test phosphorus increases, our likelihood of response actually decreases. It goes down like this is what we typically think of. And these are the areas, our very low, our medium, our high, and our very high, same thing less. So we have less than 20%. That's kind of what that curve looks like in theory and what we've seen in the past. If we throw data in it from the last 4 or 5 years, it looks a little bit like this. So instead of about 80% chance response for very low, it's about 70%. Low goes from 60 to 80 before to 62 to 70. You can see some slight changes in medium, some changes in high, some changes in very high. And a lot of this might be just we're at 48 sites or so, and these older data sets that Ron Gellerman and Jim Kerwing used are probably a lot more abundant number of sites, but we're still growing our database. So it's still showing the same downward trend as we increase in soil test phosphorus, we decrease the likelihood we'll see a response. So we look at this here, we can see, just kind of think of, because we usually think of if we add soil test phosphorus, we're not going to change yield. We're not going to reduce it, but here we do see that trend that we're, likelihood that we're increasing our yield. It goes down as our soil test phosphorus goes up. This is the likelihood that we're going to lower yield. So the lower yield by 5 bushels per acre or more. We can see that goes up as soil test phosphorus goes up. And not changing anything at all also is pretty similar. If we look at this part where these two X off here, see that's about 20 parts per million, which is pretty close to the current value of 16. Another way to choose whether they're going fertilized or not fertilized is to look at relative yield. And relative yield is calculated pretty simply by just looking at, or using these small plot trials where you put out rates from 0, 150 pounds per acre in different rate increments. You get graphs that look like this. So here at the site, we have a soil test that was 12 parts per million in this field. And we put down phosphorus fertilizers from 0 to 150, 160 pounds per acre, and you just kind of see how yield responds as it goes up. And eventually it's going to flatten out, and here we flattened out about 60 pounds per acre and required about 71 pounds of phosphorus to get there. So relative yield takes the yield that we have at 0, which is 41 bushels per acre. We take our yield at optimum, which was 76 bushels per acre, and we divide that when it gets to 0.54, which is 54% yield if we don't apply any phosphorus to this field. And then we can also look at the difference between those two lines to look at the change in yield, which would be about 35 bushels per acre if we added phosphorus to this field, which is a sizable amount. So then we're taking relative yield, we take the information from this graph and we say, okay, at 12 parts per million, we go over here, scale between 0 and 28 parts per million, we go here 0, go 12, we go up 54%, right about there. And then we kind of range that, put a line through that with a bunch of other fields, and then we can kind of see where that critical level would be. And here, in our case, in South Dakota, it's around 16 parts per million Olsen, Bray 21. More thing to think about is we don't actually have one of these for Malick. So that's one reason I don't recommend it, is because we haven't finished the research to see if Malick has a curve and what it looks like in South Dakota. So then we're just transitioning from Malick numbers to Bray and doing conversions, and sometimes those don't work out well. So we don't necessarily recommend them. So if we look at our current system, our current critical value is 16 parts per million. If we look at data from the last few years, it looks about like this. So we can see there's a general trend. So we look at our relative yield going from 0 to 100% or so. We see an increase in yield, kind of below 100% here. It kind of goes up to right around 100% in this area here. Depending on how you draw a line through there, we can see a lot of different spots of where that, critical value where we're not likely going to see a response. And these are just lines, different lines representing what that could look like. But it's about in here in the 16, 17 area that we're seeing a really low chance of increasing yield. So if we use the different models, it's anywhere between 16 and 20, an average of 17. And if we look at confidence intervals, so let's say, just doing some math and looking at ranges, you can see the ranges here. Some of them range quite a bit, but basically we're about 13 to 22 parts per million. And really, I would say if you are anywhere between 12 and about 20, you're probably pretty close to optimal. I know that's kind of big, but that 12 to 16, 18 range is pretty optimal. I haven't seen much response above those. And where this critical value is, it changes based on where you are in the US. So if we look at these graphs here, we're going to look at relative yield on the Y's. Here we're going to look at Malick 1 with a K, and this is in Virginia, Maryland, North Carolina. Look at that line there, and that critical value is 57. We look at the next one here for Arkansas for potassium and soybean. Look at that, you can see there, that one is 168. We're looking at corn in Minnesota, Iowa, and South Dakota. Not as good of a relationship for some reason. That's part of the US. We just don't get as good of one with the data that we've seen when we compiled everything. But that's still around 16 for those, those 3 state areas. So if we look at just, change in yield, so looking at relative yield, something that, numbers we kind of think about a little bit more. We can see here, this is our change in yield. So when we have an increase in yield from adding phosphorus, or when we see a decrease in yield, and this is soil test phosphorus from 0 up to about 36. So 0 for above it. So then we kind of see here, we kind of get this line right here. Whereas soil test phosphorus increases, our change in yield decreases, and it flattens out about 0 around 20, 22. But interesting about this, if we kind of go here and do math, we want to see a 5 bushel per acre increase. It's around 16 bushels per acre, or 16 parts per million where we see it. If you want less, you can go up a little bit more, depending on what your decision making is on your operation. So if we look kind of a summary of this, our critical value is really between 16 and 20 parts per million for optimal, very, very low chance of seeing any yield increase, confidence from 13 to 22, seeing that increase of about 5% or 5 bushels, 16, still that cutoff value. So not a whole lot of changes based on things kind of is shown to be similar. We might have some differences based on cropping system and rotation and tillage, but I haven't been able to tease that out. We need a little bit more data and more fields. So we have looked at using other soil tests, and we have seen that if we use soil respiration, CC, and clay, we can increase from about 68% correct to about 74%. We're still working on some of the data there. So that's kind of looking at that. Next question is, if it does respond, what rate should I apply? So then we kind of take that same information that we looked at before. We've had this graph up here where we see yield response based on the rates that we applied here, and it increases until a certain point. And then we take that certain point, we say, okay, that was about 71 pounds per acre on a 12 part per million phosphorus field to hit optimal yield. Then we go over here and put that on this graph over here to see, our 12 part per million needed 71 pounds per acre right here, and then we can kind of see the relationship that there. Then we can kind of draw lines through a bunch of other sites to kind of see what that looks like, and that's kind of what this data here kind of shows us. Something like that, as we increase in soil test phosphorus, our rate needed kind of decreases until we don't see a really strong influence. So if we kind of look at this, the soil test is also really important as far as what we use. Here is the equation for the Olsen phosphorus test. You want a P fertilizer rate. We use this equation right here to kind of come up with it. And our Bray one is this equation. You can see they're pretty similar. However, these two numbers do differ. And it's important that if we use an Olsen phosphorus test, that we use the Olsen phosphorus fertilizer rate equation, same with Bray phosphorus, and we don't have one from Mehlich. You'd have to convert the Mehlich to an Olsen or Bray number, which has some issues, which is one reason we don't necessarily recommend it, and why if you ask your soil test which one they're running, and sometimes you have to make sure that they're running the one they're telling you and not just converting it, so that's important too. But you can see here, if we do use this number for Olsen phosphorus, we got 34 pounds per acre. And if we use, those same exact numbers for the Bray phosphorus test, the same parts per million, we get 56 pounds per acre. So if I were to do the Olsen test and then use the Bray equation, I'm going to over fertilize what I need. However, if I use the Bray equation and use the Olsen, we're likely to under fertilize. So it shows us that that does make a difference as far as what equation and what test we use, because those are the ones that it's correlated to. So it's important to know, to ask your lab, what test did you run, so you can know what equation to use to make your fertilizer decision as far as rate goes. Sampling depth is another important. If we look around us, the states use anywhere from 0 to 4, 0 to 6, or 0 to 8 inches. So it's important that here in South Dakota that when we do go out, our recommendations are based on a 0 to 6 inch sample for P and K, and then for sulfur and nitrogen, it's based on a 24 inch sample. So that's really important. pH, pK, micros, nitrate, nitrogen, and also mobile nutrients, nitrate, nitrogen, and sulfur for that 6 to 24. Need 0 to 6 and 6 to 24 inches in depth. So it's important to remember that. And when we're sampling, some states do 0 to 8. I can't tell you why. Western sites do 0 to 12. This depends on how their recommendations are set up. Ours in South Dakota are 0 to 6. So if you need to make sure when you're soil sampling, if someone's doing it for you or you're doing it, that you're doing the right depth. Because if you're going to 0 to 8, you're likely going to be decreasing the amount of phosphorus you're finding, which is going to change your recommendation to maybe be too low. And it's also important because when we're doing all this research, looking at relative yield, looking at change in yield, looking at the rate we got at each field, we use a certain depth. The depth that we use is 0 to 6. If we want to look at 0 to 4, for other ones, we need the data behind that. But we are looking at that 0 to 4 inches because some people do have that question in no-till, where we do see it's kind of a stratification of nutrients. I hope this update on some of the phosphorus soil testing, as well as just some basic information on soil testing and why it's important to know what soil test your lab is using, so you can then use that correct information to then use the right equation to come up with a decision regarding rate of phosphorus fertilizer application, understanding why we use Olsen tests most of the time, Bray when we're low soil pH. Mehlich we're still working on, hopefully we'll get some funding to do more on the Mehlich 3, as well as some other phosphorus tests that are newer, to see if we can improve some of our phosphorus fertilizer recommendations for both till and no-till and different long-term cropping rotation systems and things like that. I look forward to working with you all in the future, and as always, if you have information or would like to do a soil fertility trial on your field, go ahead and give me a call. You can see right here my different contact information. Thank you for your time today.